I'm delighted and in fact feel privileged to participate in this symposium. Unlike most of them, on the other hand, I cannot consider myself to be one of these superb students of Michel Foucault. But I am a student of his former students, so perhaps my presence here serves as an example of his impact on not just one generation, but many generations of catalytic researchers. A couple of years ago, Professor Foucault organized a symposium, and he sent to all his teachers the following words of wisdom. These words meant a lot to me when I read them, because at that time, my research group was beginning a conscious effort, moving into the area of catalyst preparation with the hope of using catalyst preparation as an experimental tool to understand catalytic materials. Our overall objective is trying to bridge the relationship among preparation, structure, and chemical properties in the loop in which we're trying to use catalytic preparation to get at certain structures and then try to relate those structural properties to downstream chemical properties in order to address general questions that are posed here. Now, the general approach that we have adopted is the use of catalytic aerogels. Let me outline that approach for you. We first use alkoxide precursor to make gel, and the procedure there is simply to go through hydrolysis and condensation, giving us a diphasic material, which is a solid encapsulating the solvent. The solvent is then subsequently removed by supercritical drying, giving us a product that's referred to aerogel. Now, we see this as a very powerful approach because it controls the dual advantage of the issue of control, because a lot of parameters up here on this part of the diagram that are at our disposal, and by changing this parameter, we have some control over the materials, and then on top of that, by using supercritical drying to remove the solvent, and thereby eliminating the liquid-vapor interface, we add on to the advantage of control another level advantage, which is preserving the integrity of the morphology of the catalyst. So what I try to do today is to give you a snapshot of how this approach can be used in looking at two different systems, namely the zirconia silica system and the zirconia sulfate system, which we just heard a little bit about. The common theme in these two parts of the story is that, well, we're dealing with zirconia, but the other part that I want you to be interested in is really to do in a one-step preparation of introducing a dopant, be that a second oxide, such as silica in the top case, or sulfate, which is another dopant. And the challenge in the two problems is different in that in the first one, we're trying to manipulate precursor reactivity in terms of controlling the homogeneity or the lack thereof of the product, versus the other challenge in the second half of the problem, which is to use the preparation as a means to understand catalyst activation. So let's start looking at the first one. In the zirconia silica problem, what we're trying to ask is the following general question. If we're going to try to bring two oxides together in a mixed oxide, what we have to do is to start with two precursors indicated here as A and B, and then we let the hydrolysis and condensation take place, resulting in two products. Now, one can easily imagine that the two alkoxides have very different reactivities. Let's just say that one is more reactive than the other. Then you're going to have a situation over here, which what we refer to as a segregated mixed oxide, in the sense that we first have a core of the more reactive species with the less reactive species coating on the outside, in which case this preparation is not unlike a two-step impregnator procedure. On the other hand, if the two alkoxides have similar reactivities, then what we get will be a homogeneous oxide at a micro scale, meaning atomically we have the two oxides that are very well mixed. The issue is really not whether you want a homogeneous oxide or a segregated oxide, because that decision is based on the chemistry that you want these materials to catalyze. The point is by controlling the precursor reactivity, one has a choice as to the final state in terms of the distribution of the two components in this mixed oxide. So what strategy do we have in order to go whichever way we choose to? Well, it turns out there are four common ones for matching precursor reactivities, and I have summarized them for you on this slide. For the specific example of zirconia silica, the two precursors that we use is zirconium propoxide and silicon ethoxide. Okay? It turns out in this case, the zirconium precursor is the much more reactive one. So if you do not do anything, what you're going to have is going to have a segregated oxide with the zirconia encapsulated in the silica growing around it. However, we can play the following games. We can use a more reactive precursor, such as the ethoxide instead of ethoxide, to speed up the less reactive precursor. Another way to speed it up is to employ a trick called prehydrolysis, in which you can react the silicon precursor with water, giving it some functionality, and then allow it to participate in the condensation chemistry. The flip side of that is to slow down the more reactive precursor, in this case the zirconium propoxide, by complexing it with the acetate and slowing the reactivity down. And finally, with the hope that the two alkoxides have different sensitivity towards temperature, you can do the preparation at a different reaction temperature. We have done all four, but with the time, I was just going to spend a little bit of time talking about prehydrolysis as an illustration of how such a strategy will work. So let me show you the recipe with which we carry out two preparations. On the left is a standard non-prehydrolyzed sample, which we call NPH. And in here we simply mix all the precursor in one step, add water and acid to it. The gel will form, and we go ahead, make an alcohol gel, supercritically dry it, giving us the aerogel. On the right, where we have the prehydrolyzed sample, all we did was to take the separate precursor, add water to it, allow it to prehydrolyze for 10 minutes before adding the zirconium precursor. And what happens right away, as you notice from this slide, is there a difference in gel time. Now, gel time physically corresponds to the point where you have a change in viscosity in the salt to gel transition, meaning the network has built. And then by changing prehydrolysis, you change gel time. Now, that in a sense is unfortunate because we have found, as well as others, that gel time itself affects the morphology of the calculus. So what we have to do is to first find a way to uncouple the effect of gel time from that of prehydrolysis. And what we did was to develop a synthetic protocol in which we have 3 pairs of samples by controlling the amount of acid we use in the preparation. One that's entirely without prehydrolysis, one that is with prehydrolysis. So at each gel time, or roughly constant gel time, we can uncouple the 2 effects. So from this point on, your attention will be focused on 2 series of samples, one without prehydrolysis, one with 3 varying gel times. Well, the first thing we notice is, yes, prehydrolysis does change the response of the sample in terms of the calcine BET surface area, calcine under the condition show as a function of gel time. Without prehydrolysis, gel time does not affect the surface area much, but with prehydrolysis, with increasing gel time, we have a significant decrease in the calcine BET surface area, which incidentally behave exactly what you would expect with pure zirconium. It turns out this decline in surface area at high gel time is caused by a shift in the pore size distribution of these samples determined with nitrogen adsorption desorption. So what you're seeing are 3 panels of different gel time. The filled circles are the non-prehydrolyzed samples, and the open circles, the open squares, are the prehydrolyzed samples. So with prehydrolysis, what happens is the material behaves as if it's pure zirconium only. So what happened to the silicon? Well, we believe that with prehydrolysis, we actually successfully match the reactivity of the 2 precursors such that the whole material gel as if its silica is not present. So this little cartoon summarizes what we think is happening. Without prehydrolysis, we have mismatched reactivity. The zirconia gel first, while the carbon particles are formed first, followed by the silica on the outside. When you match the reactivity, you have a homogeneous sample. One quick evidence of that is that if the silica is indeed on the outside of the zirconia, then we should be able to see the signature of the silanose stretch, which we did see. So when we look at the pair of samples at the long gel time, we did see a high signature of silica on the outside when we did not make the attempt to match the reactivity of the 2 precursors. Now, the punchline, of course, is what is the catalytic significance? The implication is anytime we try to match the precursor reactivity so that they are better mixed at a microscopic level, the acidity goes up as measured by 1-butene isomerization, and anytime we don't do that, the sample is less active. So in all situations in which we have made an attempt to match reactive precursor reactivity using either hydrolysis or add modification, which is the strategy to slow down the zirconium precursor, or using a more reactive precursor, we see a corresponding increase in the isomerization activity. So that ends the first story. I still have 5 minutes left. And with that, I just want to quickly walk you through another preparation, and namely the introduction of sulfate into a zirconia system. Now, as pointed out by Enrique, there were 100 papers published in the literature, and it turns out that the conventional way of making this preparation is to introduce the sulfate either through immersion in sulfuric acid or incipient wetness impregnation of ammonium sulfate on the heated but not calcined sample, i.e. a lot of preparations have been done on the hydroxide. With our preparation, we actually have flexibility of introducing the sulfate either on the calcined aerogel, or what I'm going to show you in the next few slides is to introduce the source of the sulfate again in a one-step approach during the preparation step. Now, what that brought us is the flexibility of controlling the sulfate content and the location with which the source started. So we can now, by just changing the amount of sulfuric acid, we can vary that quite easily, and we can put the sulfate inside the material and therefore follow the activation of the samples a little more carefully. So let me start by showing you the activity data in this case. I feel sheepish showing the slide because the rate, in fact, is reported on a non-Stanford unit gram. But let me assure you that the variation in surface area among all these samples is not significant at all, so you can immediately read meter square if you want. The point I'm trying to make, though, is by varying the sulfate loading from 5 mole% to 10 to 20, we were seeing very different activation behavior as these samples were heated all the way from 673K to about 923K. With 5 mole% sulfate, we could not activate the sample at all. With 10 mole% sulfate, the sample became active at about 773K, went to a maximum, which is significantly more active, and then less active with increasing activation temperature. With a 20 mole% sample, it's a little more complex, but in fact has 2 maxima in the activation. 2 points. First of all, since the sample response to activation is very different depending on preparation method, comparison of literature data must be borne with that in mind. The second point is with this preparation method, we have now found certain windows which allow us to look into the difference of a catalyst as the activity goes up and down, and therefore hopefully have a handle of what is causing the increase or decrease in the activity. So let me just show you in the last 2-3 view graphs what do these samples look like. Structurally, they do the following. These are X-ray data as a function of activation temperature at the 3 concentration of sulfate we work on. First of all, as a reference, if we have no sulfate at all, the zirconia aerogel goes through a amorphous to tetragonal to monoclinic transformation with increasing heating as shown here. When you introduce sulfate to it, it retards both the amorphous to tetragonal and subsequently the tetragonal to monoclinic transformation. There's no surprise there whatsoever. The interesting thing, though, is every time we observe this maximum in activation, it always corresponds with a crystallization of zirconia. In fact, if you look at the reverse of it, until we see the crystallization of zirconia, we could not activate our catalyst. Now, one can argue which is the head and which is the tail. The point being, it seems that a crystalline zirconia is necessary to support an active sulfate species. Now, to follow that a little bit more closely, we look at the infrared spectra of each of these samples, again, looking in the window where we go from an inactive to an active sample, because now we can make different slices across the activation. For the 5 mole percent sample that we couldn't activate, we found out that we have a peak that's around 13, 16 wave number that we now identify to be a signature or fingerprint for an inactive species. For the other 10 and 20% sample, anytime we have increase in activity as a function of activation temperature, it was always accompanied by the appearance of a sulfate feature that is falling on right around 1380 wave number. So there is a very good signature to look at an inactive sulfate group versus an active sulfate group. Finally, to confirm what we were just told, that now that we have a way to look at activation carefully, we can also quantify the ratio of Bronsted to Lewis site and the presence of Bronsted site as a function of activation, as a function of sulfate loading, and yes, all active catalysts have Bronsted acidity. So Bronsted acidity is a necessary condition to have N-butene as dominant reactivity. There's some details as to how well the activity pattern tracks the Bronsted acidity pattern, but this is something that I'd be happy to talk about if the question arises. So I'm just going to summarize in words what I have told you. And the message in the second part of the talk is simply the following. By preparing a series of catalysts differently, it basically gives us 4 places to look. We didn't find new catalytic chemistry, and I don't think we even make new catalysts. But again, I think by a different preparation method, we have learned a little bit about the activation of this process of material. So to conclude, I would like to bring back the slide that started all this. And I hope I have convinced you in today's presentation that, yes, catalyst preparation does give us a chance to look at certain catalytic behavior in a way that's not probably open to us before. And the bottom line is, it's fun, it's effective, it gives you a lot of flexibility, it gives you a lot of different ways to look at a problem, and I leave that with you, and thank you for your attention.
Any questions before? Yes.
You find that you need crystalline zirconium, it would seem that the differing reactivities would be of no power. So you should be able to make a sample where you get crystalline zirconium more easily with the pure oxide react different ways.
That is actually true. So like I said, we didn't make a better catalyst. Now that we know what does it take, yeah. And so by introducing sulfate into the pot, we are basically just delaying that event. We are not enhancing it. But it just allows us to track at what time it happens and have evidence of finding that correlation. So if indeed, but like I said, I don't know which is the head and which is the tail. So if I have a need for a crystalline zirconium, I can dope that sample with a small amount of silica, and I don't really care what the silica is, as long as 1 is not that well mixed, 2 is not present in such high amount to prevent the crystallization upon heating. You're absolutely right.
The heating process by which you observe this transportation is also one that is removing water from the surface of acetonium. And the main difference between the Lewis acid and the Bronsted acid site is that one is hydroxylated and the other one is not.
Yes.
So is it possible that it is a coincidence that the temperature at which the transportation takes place, it's the one at which you begin to remove this extra layer of water that you may have in the system?
In our system, no, because I should have qualified it. In situ, the trip data trying to find a signature for the active sulfate group was done in situ. And it was the catalyst was pre-treated exactly the same way it was pre-treated in the reactor. So in terms of surface hydroxyl inventory, that's no problem there. But I think your point is well taken is we compare our sample with the sample that we put the sulfate on a zirconia that has not been previously hydroxylated. Yes, one has to be very careful to keep track of hydroxyl inventory. And in fact, if you have a lot of water around, in fact, for the 5 mole percent sample that is totally inactive or totally activated over that range, that sample actually has Lewis acidity. But there's no Bronsted acidity. So I don't know whether I addressed your question.